Hi there. In this video, we're going to talk about differentiation of complex functions, and we're also going to look at differentiation in the complex plane. This culminates in what's called the Cauchy Riemann equations and how they're used to establish if a complex function can actually be differentiated. So traditionally, we would have some function of x and the derivative f prime x, also called dy dx, is merely defined as the limit, okay? We have the limit of some incremental change, we'll call it delta x, that approaches 0. It's often called h in many different textbooks. And you know what's being taken the limit of is usually some function, the incremental change in the function, subtracted by the function itself, and divided by the increment. So this is standard elementary calculus, okay? So how does this apply to the complex plane? So let's try and establish what we're talking about when we want to understand the derivative of a complex function. We know that we have two planes, right? We have the z plane. This is the z plane. And it has a complex variable. And maybe there's some line, okay? There's a line that's defined. And of course, each point along this line will have a corresponding x and a corresponding y, real and imaginary parts. And then this function is transformed in some way into the w plane. And the link between the z plane and the w plane is the transformation equation. So if we have something with respect to z, okay, so this is z, okay, a collection of points of z. So when we speak about delta z, so delta z is some differential change in this function that's in the z plane. So this function z, okay, this collection of points, would have had some equivalent collection of points, w, associated with each one of them. So the moral of the story is that this differential change delta z has associated with it some differential change delta w in the w plane, okay? So when we speak about derivatives in the complex plane, what we're asking is, when we have some differential change z, complex variable z, how much does w change by? So what is the rate of change of w as z is changing? So this is essentially what we want to establish in terms of the derivative. And we would consider the limit as delta z approaches 0. So we also know that w is equal to some function of z, okay? So we actually want to determine dw dz. That is the derivative. How much does w change when z changes? So how is it defined? Well, it's defined in exactly the same way as the traditional derivative is defined. So we would have something like f prime z, okay? And that would also be equal to dw dz. So everything that is written here also has an analogy in the complex plane. So dw dz is equal to the limit as delta z approaches 0, and instead of x plus delta x, what we would have is f into z plus delta z minus f of z divided by delta z. So this is the derivative of a complex function, okay? So the same differential rules apply. So if we have f of z is equal to z squared minus 4. So what is f prime z? Okay, what is f prime z? So f prime z is simply 2z. So this is all easy and straightforward. So the question and where the complications arise is, does f prime z actually exist? So that's the question. That is what we actually need to establish, okay? So if f prime z exists, that's all well and good, okay? Then the other question is, does f prime z have a unique variable? In other words, is there only one derivative f prime z? So there's two things that we actually need to ask ourselves. The first one is, does f prime z exist? And the second question is, is f prime z unique? So does this actually is asking, is there only one derivative? In this case here, we have 2z, right? So that's just one derivative. So we need to establish all these things. So what the Cauchy Riemann equations do is actually help us, okay? So f prime z exists. So in general, we have fz, and fz is actually called an analytic function. So this terminology is used quite a bit. It's an analytic function, and sometimes the word regular is also used. It's a regular function. So in general, the derivative will probably exist if it's an analytical function. So what is an analytical function? Analytical function means that at a certain point z, we can choose some random variable here. So we have a point. And at that point, we have a defined value of z. Okay, that's number one. And number two, it has a single value. Okay, that's x and that's y. So we have a single value. That means we have one single real and imaginary part. So if that happens, then it means we have an analytical function. So an analytical function is likely to have a derivative. So that's the first one. Okay. So we need to say a function is analytical. So the second one is f prime z unique. So that's where the Cauchy Riemann equations come into play, and it's quite straightforward to actually derive. So we have w in the w plane, and we said that's u plus jv. And we have delta w, some incremental change that would be associated with an incremental change in u and an incremental change in v. We have z as well, and that we have also described as being x plus jy. So an incremental change in z is an incremental change in x and an incremental change in y. So if we are saying f prime z, okay, then what we're actually asking for is dw dz, and we're asking for the limit as z approaches 0 of delta w divided by delta z, okay? And what's delta w? Delta w is this delta u plus j delta v. So that's delta u plus j delta v, and then divided by delta z, and delta z is delta x plus j delta y. So now we have this thing here, right? Okay, I should also write the limit in front. So this is the limit as z approaches 0. We don't actually have z in this thing, okay? We don't actually have z. But we do have x and y, and we know that actually z is made up of x and y. Sorry, there should be a delta there as well. So what we can do is that we can break up this specification that delta z must approach 0, and we can split it up into two, okay? So we can split it up and say delta x should approach 0. Okay, that's not written very well. Let me just write it a bit better here. We can split it up and say that delta x can approach 0 and delta y can approach 0. So that's what we're going to do. We're going to do both, but we're going to do it one at a time. We're firstly going to let delta x approach 0, then we're going to let delta y approach 0 of this particular term that we have here. So if we let delta x approach 0, so let's write that down as the first step. So we let delta x approach 0. So when we do that, what we're left with is the limit as delta y approaches 0, okay, because we've already taken the limit, of delta u plus j delta v divided by j delta y. Okay, and remember what we're actually calculating. This is f prime z. Let's just divide this. So the limit as delta y approaches 0, we have delta u divided by delta y and delta v divided by delta y. So let's just do the second term first. So this j divided by j is just going to give us 1. And then what we have is delta v divided by delta y. And now we have 1 over j, right? We have delta u divided by j delta y. So 1 over j, what we're going to do is multiply this by j over j. Remember that j is the square root of minus 1. So we have 1 over the square root of minus 1 times the square root of minus 1 over the square root of minus 1. So the square roots essentially give us cancel out. So we have basically square root of minus 1. Essentially, we have minus j. So that's what's left. So we have minus j. So 1 over j becomes minus j. And we have delta u divided by delta y. You would remember from the previous videos that u is a function of x and y. So u is some function of x and y, and v is also a function of x and y. So this is actually multiple variables. And you would know now, if we're dealing with multiple variables, we have to deal with partial derivatives. So this delta v, delta y, as we take the limit as delta y approaches 0, becomes day v, day y. And this j becomes, well, it stays the same, and then delta u, delta y becomes day u, day y. So this is the first equation, important equation. That's part of the Cauchy Riemann equations, but we still need to get there first. So we let delta x approach 0. That's what we have done. So what we're going to do now is the reverse. What we're going to do is we're going to let y equal to 0. We're going to let delta y equal to approach 0. So if we do that, okay, there's our original equation. If this approaches 0, what we're left with is just delta x in the denominator. We can write that out. So we have the limit as delta x approaches 0 because we have taken delta y. And we have delta u plus j delta v divided by delta x. We can divide it as we had done before. So that's the limit as delta x approaches 0 of delta u divided by delta x. That's delta u divided by delta x. Then plus j delta v delta x. And in the same way, we get simply day u dx plus j day v dx. So we have f prime z and we have f prime z. But we have two equations, yeah, right? We have two equations for f prime z. So if f prime z has one derivative, in other words, has a unique derivative, remember that's what we're considering, is f prime z unique, okay? Does it have one derivative? So if there is only one derivative, it means that these two equations must be the same because they are both f prime z. So we have to make them the same, essentially. We're making it's the same as a condition. So we're going to say that day v day y minus j day u day y is equal to day u dx plus j day v dx. We will now equate the real parts and the imaginary parts. So if we equate the real parts, so what that means is that day v day y is going to equal to day u dx. Okay? And it's also going to mean that day v dx is going to equal to minus, right? There's a minus sign there, day u day y. So if we remember our example from earlier, we had f of z is equal to z squared minus 4 then we can show via this condition. By the way, this is what's called the Cauchy Riemann equations. Cauchy Riemann equations. So these two collectively form the Cauchy Riemann equations. So let's apply it to this example. Okay, let's get everything in terms of x and y and u and v and all this stuff. If we do that, we get f of z is equal to x plus jy squared minus 4. Remember that this is what z is equal to. Then if we expand it out, we get x squared plus j 2xy minus y squared. Remember, j squared is minus 1. Then minus 4. Grouping the real and imaginary terms, we get x squared minus y squared minus 4. Then plus j 2xy. So that means that u is equal to x squared minus y squared minus 4, and v is equal to 2xy. So we can take day v, day y. So let's do that. Day v, day y is equal to just 2x. Okay, this should equal to day u, day x. So let's compute day u, day x. Day u, day x. That's just equal to 2x as well. Remember that this y squared and this 4 are constants since we're taking a partial derivative. And lo and behold, they are equal. So we can check the same with the other as well. We can take day v, day x. So day v, day x is equal to 2y. Right? We can easily see that. And now we have to compute minus day u, day y. So minus day u, day y. So that's minus and day u, day y. So we have, well, that would be a constant, so 0. And then that would also be a constant. So we just have minus 2y. And that gives us plus 2y. We can see that that and that is equal, and that is equal. So this Cauchy Riemann equations is actually what we use to establish if the derivative is unique. So if they're not the same, obviously it means that we're going to have a problem. We're going to have an issue there. So these are the two key things. Does the derivative exist, and is the derivative unique? So tied in with the fact if the derivative exists, we're considering an analytical function, also called a regular function. And to establish if the derivative is unique, then we're looking at the Cauchy Riemann equations. So thank you very much for watching.